All right, well, good afternoon, everyone, and welcome to today's EOL seminar, for which I'm pleased to introduce Dr. Sebastian Hoch. Dr. Hoch is an atmospheric scientist with a broad background in observations of complex surface and atmospheric boundary layer processes. He received his doctorate in natural science at the Swiss Federal Institute of Technology in Zurich, Switzerland, based on his studies of the stable atmospheric boundary layer and the surface energy and mass balance of the Greenland ice sheet. He then moved to the University of Utah, where his postdoctoral studies, funded by the Swiss National Science Foundation and the Army Research Office, investigated gradative cooling processes in complex terrain, both by means of direct observations via the meteor crater experiment and Monte Carlo radiative transfer simulations. His growing interest in mountain meteorology and the use of wind LiDAR technology led to participation in field campaigns such as the NSF and DoD-funded Persistent Cold Air Pool Study and Matterhorn campaigns in Utah, the second meteor crater experiment, and the meteorological observations accompanying the Utah Winter Fine Particulate Study. Dr. Hoch has applied his observational expertise to investigate air quality applications such as particulate matter accumulation in persistent cold air pools, dust emission, dust and chemical precursor transport, and fire weather in a variety of terrain. International collaborations and research visits to the Swiss Institute for Snow and Avalanche Research, EFPL, based on his expertise in wind LiDAR observations, led to a joint field campaign in the European Alps studying snow accumulation patterns in complex topography, wind energy potential, and orographic clouds. More recently, Dr. Hoch has studied the life cycle of coastal marine and cold pool fog via Matterhorn fog, sea fog, Fatima, and CFACT experiments, focusing on the radiative feedback on microphysical and thermodynamic processes and turbulence. Dr. Hoch has participated in over 20 field campaigns and co-authored more than 70 journal articles. He holds an adjunct appointment at the University of Utah and advises master's and PhD candidates as well as postdocs. As the lead scientist of EOL's Integrated Surface Flux Facility, Dr. Hoch oversees observational research on surface-atmosphere exchange processes. Within NCAR, he advances Earth system science by facilitating successful field observations proposed by university PIs and building new collaborations across NCAR labs. He strives to update available instrumentation to meet the needs of current and future investigators, ensuring ISFS remains at the forefront of surface-atmosphere exchange research. Please join me in welcoming Dr. Hoch for his seminar on playing laser tag with clouds.
I wanted to thank Sarah for the introduction and also Dylan, who made this really nice flyer for this presentation. So good afternoon, and thank you for coming and online and in the room, and your interest in the seminar. As Sarah alluded, my interests are fairly broad, and based on my recent presentations at conference, you might have expected a talk about fog or radiative cooling. But today I have the opportunity to talk about an observational study of a very fascinating, at least to me, fascinating phenomena, and those are banner clouds. Before I start, I want to acknowledge my co-authors. Those are Professor Volkmar Wirth and his PhD student Marius Thomas from the University of Mainz, and our Swiss partners, Hendrik Huwald and Michael Lehning. What are banner clouds? Banner clouds are a counterintuitive phenomenon, and that's why they are so fascinating to me. So when we think about orographic clouds typically are expected to form on the windward side, as flow in moist air is pushed towards the mountain barrier, is lifted, cools adiabatically, and the moisture condenses into clouds. Banner clouds, however, and I'm going to play this animation one more time, are confined in the leeward side of a mountain, are therefore counterintuitive. So these mountains typically form on high pyramidical peaks, like in the Matterhorn of Switzerland, but they can be observed in the Himalayas, on Everest, or also the Grand Teton in Wyoming. They persist on timescales longer than the timescale it would take for a parcel to cross a mountain barrier. And they're very stationary and persistent and connected to the lee side of the mountain. And their vertical extent, or their horizontal extent can vary from being very close to the mountain to forming a very long extended banner. So with just these observations, we can infer that there are specific dynamical processes that must cause stronger lift in the lee than on the windward side of the mountain, so that the water vapor condenses into a cloud on the lee. So why are we interested in banner clouds? As I said, it's a counterintuitive phenomena, and that triggers our intellect. We want to understand how the atmosphere works, what it tells us. And they result from very complex flow structures, so this might offer actually a good benchmark for our numerical weather models. Their circulations affect air transport in mountains, and the circulations associated with them lead to differential transport of hydrometeors and differential snow deposition that have hydrological impacts. So I already introduced you to what a banner cloud is and some visuals. Next, I want to kind of revisit what we know about flow interactions with terrain. Then I want to introduce you to some large ADIA simulation, idealized simulations about the banner cloud phenomena before introducing you to our observational study. These observations are then used to validate high-fidelity model simulations, and the results from these simulations and observations will be used to again revisit our theoretical guidance. So when we think about what controls the interactions of flow with terrain, there's topographic and flow characteristics that dictate this outcome. One is the wind speed, then the stability of the flow. The stability is a measure of how much the atmosphere resists to being lifted over the mountain. So if the stability is high, there's more resistance to lift than if the atmosphere is neutrally stratified. And then, of course, we have terrain features like the height or the obstacle width that affects it. So these characteristics can be combined into non-dimensional parameters. One is the inverse fruit number, n. That is the Brunt-Väisälä frequency multiplied by the height of the obstacles divided by the wind speed, and then the aspect ratio of the topography. So what does this outcome look like? So when we have a large n, we have high stability or weak flow, blocking occurs. So the flow really resists going over the mountain, and it gets blocked or is forced to move around the terrain obstacle. On the other hand, if we have a very small n, it's easy, even for weaker winds, typically we have then strong flow or we have weak stability, it is easy for the flow to surmount the obstacle. Often we see flow separation across the ridge lines and returned circulation in the lee. So these interactions can be summarized in a regime diagram between looking at the aspect ratio and this inverse fruit number. And when we have weak stability or strong flow, so we have this weak n, the flow tends to follow the topography. So the flow streamlines follows the topography. Now, if the mountain obstacle becomes steeper with a higher aspect ratio, we see something that is called leeside separation. So the streamlines disconnect from the topography, and we often see recirculation in the lee. Now, for a given steepness of a mountain, if we increase the stability, we come into a regime where gravity waves occur, and they pull down the point where the separation from the separation of the flow occurs along the slopes. So if we look at banner cloud occurrence, Prestel and Weird have shown with numerical simulations of a idealized peak that the potential for banner cloud is really within this leeside flow separation regime. And how do these look like? So let's look at some of the idealized simulations that are available. We see in this case, we see in the vertical cross section, we see still very strong flow on the windward side, but we also see this nice large leeside eddy that is occurring with large upward velocities in the lee. If we look at the horizontal cross section, we see nice organization, two counter-rotating eddies in the lee of the mountain. So when we combine these, we basically see that these circulation are a footprint of a leeside bow-shaped vortex. So the flow comes around the mountain, moves in the back, and then rises in the lee. And this is the typical circulation that we see when we have this leeside flow separation. Now, if we look at these vertical velocity fields, however, we still see that the vertical velocities are highest in the windward side. So why do we see cloud formation in the lee? Now we can, for cloud formation, the wind speed, the vertical wind speed, of course, is not as important, but it's actually the integrated lift over the path of the air parcel that leads to the adiabatic cooling and the condensation, the potential of clouds. So we can introduce a tracer in these simulations called Lagrangian lift or vertical displacement, and we can plot a field of this vertical displacement for these circulation patterns. And what we see that there's a strong asymmetry between the windward and the leeward side, and we see that the vertical displacement is just in that area where we expect banner clouds to occur. So this vertical displacement almost is a potential for banner cloud formation, as it's kind of the integrated lift. So now the question, of course, arises, how does this change with flow conditions? So if we look at a homogeneous wind field or a shear wind field, we actually see that the streamlines and also the vertical velocities in the lee of the mountain change dramatically. However, when we look at the effect of these, the net effect into the vertical displacement, we see actually that the shape and the area where the vertical displacement is maximum remains in the lee side of these steep pyramidical peaks. So it seems that the potential for banner cloud formation is really a robust feature. So then we can also look at comparing an idealized simulation with real-time topography. So here you see results for an idealized pyramid, and we see these beautiful organized counter-rotating eddies in the lee in this real area with high vertical velocities organized here in the center. But if we look at results from the realistic topography, we see a significant loss of all of the symmetries of these leeside eddies. And we see a loss of all these coherent vortex structures. But yet again, if we compare the vertical displacement of an idealized pyramid with the realistic topography, we're surprised, and again, see that this vertical displacement, this area of the vertical displacement, still remains within the area where we expect a banner cloud to form. So that potential for a banner cloud is really a robust phenomenon, and it is maintained in the lee side of these peaks. So these are all model results. And the model results really stress the importance of flow separation and the lee side flow reversal, and really stressed that vertical displacement as key ingredients for banner cloud formation. And we've seen that this vertical displacement is actually very robust with under different flow conditions and geometries. But then as an observationalist, I have to ask myself, how realistic are these model results? And how do they actually compare with observations? And then what would be the right tools to investigate these circulations in the atmosphere at high altitude? Volkmar was presenting on these banner clouds and idealized observation at one of the MountainMat conferences in the past. And I was really fascinated by them, and there was a little bit of jealousy involved too, because he was studying these high elevation peaks, while meantime, I was calling myself a mountain meteorologist, but I studied what people called a hole in the ground. So, nevertheless, this was a super fascinating experiment, the second meteor crater experiment supported by EOL, where we studied katabatic nocturnal flows forming on a plain surrounding the Arizona meteor crater that impinged on the crater lip and led to downslope windstorm type flows into the crater basin. And in order to investigate these, we decided to use wind LiDAR to detect these. And here you see actually Bill Brown with, I think, his second deployment of the LiDAR, and you see our LiDAR there in the bottom of the meteor crater. So a quick rehash, not all of you might be users or LiDAR experts. So a wind LiDAR shoots a laser beam up into the atmosphere. That light interacts with aerosols, scatters back light to the sensor, and based on the time when the backscatter is received, we can gate this into a range gator so we know where in the atmosphere that signal is returned. Now, a Doppler LiDAR or a wind LiDAR can actually resolve by the Doppler shift of the light the speed of the aerosols that produce the backscatter, whether they are advected towards or away from the instrument. So we can actually resolve the wind speed based on the Doppler shift with which these aerosols are moving. So we get a radial velocity, so always a long beam velocity from the wind LiDAR. Now, when we play laser tag with clouds, we see that clouds are very good reflectors. They are basically dense aerosols, right? So we get a really good return signal. So it's very easy to look at the velocities at the edges of clouds. However, the downside is they also attenuate the laser light, so you cannot see beyond a cloud. So that we need to keep in mind. These LiDARs have hemispheric scanners, and you can do different scanning patterns. So one common is the range height indicator. You take just a vertical slice, you're scanning, you're keeping the azimuth constant, you're varying the elevation, or you do the opposite. You vary the azimuth angle at a constant elevation, you get kind of these cone types scan called PPIs. Now in the meteor crater, what we did is we combined two RHIs, one from Bill's LiDAR on the crater rim with the second LiDAR in the crater bottom. And doing that, having them scan in one plane, we see from one location, we see the radial velocities right from the two individual LiDARs. And these signals basically result from the flow within this plane. And so we can do some trigonometry and derive the horizontal speed within the plane and the vertical speed within this plane. And this is what we did. And here I show a quick animation. So the flow is coming to the right here, and you see this stable layer moving over the crater and impinging and producing a lot of fascinating flow phenomena that I'm not going to discuss here in detail. But Volkmar, when he talked about these cool clouds, saw me looking at complex flow terrain, and so it flows in terrain. And so we decided together whether it would be a good idea to combine forces and actually run a field campaign in the Alps. So if you look at this terrain, it's a lot more challenging than the northern plains of Arizona. And we had to ask ourselves some really good questions, whether this was even feasible. So the biggest question was, can a LiDAR probe actually work at elevations where we expect these banner clouds? At these elevations, do we actually have enough aerosols to provide the backscatter signal and therefore resolve these radial velocities? And are there even accessible vantage points where we can deploy such an instrument? And in complex terrain, it's like, what are the land access and permission issues associated with that? So I was at a short sabbatical at EPFL in 2019. I was working on leeside eddies and snow deposition in the lee on slopes, and had access to the EPFL LiDAR. And we decided to see, well, what can we see if we plug in that LiDAR at the power outlet closest to the east face of the Matterhorn? So that outlet is actually owned by the cable car station at Trockener Steg, and that's where we ended up plugging in the LiDAR. We scanned in, we programmed a couple of scans, one of which was a RHI, so a slice through the summit pyramid of the Matterhorn. And here you see what we've seen. There's actually not very much on this picture, but if you look carefully, there are some exciting features. So in the first few hundred meters away from the LiDAR, you see the so-called the clear air return. So these are the returns from aerosols in the atmosphere. So this is the data that we would have used in the meteor crater. And then far away at the slopes of the Matterhorn, we see these hard target returns. So these are zero velocity with high reflectivity returns. But sometimes it's nice to focus into the little details. So we were really excited in the upper part of the banner cloud to resolve that strong flow, that is that westerly flow indicated here, that gives you the flow component towards the LiDAR. We saw a strong flow at the upper side of the banner cloud. And even more exciting were these little red and yellow specks that you see here on the underside of the cloud. So this is flow away from the LiDAR. So we're actually resolving this circulation patterns and that return flow in the immediately of the Matterhorn. So with this data, we felt comfortable to think about a proposal. We definitely knew we needed a longer range, or we needed to have the LiDAR closer to the mountain, and we likely needed an instrument with higher power. So, but we thought with this data that we were able to have sufficient arguments to propose a field campaign. And DFG, the German Research Council, ended up funding our proposal with some significant cuts, especially to my contribution and the observational side. But we got funding in late 2019. And then, unfortunately, COVID threw a wrench into everything, right? And we had to postpone a campaign. Meanwhile, Marius got hired as a PhD student, and he started doing idealized model results with the actual Matterhorn topography that I showed you earlier. And after the pandemic, in 2023, actually in spring 2023, decided now it's our chance. Let's come together and run a field campaign. So we have developed an observational strategy. We had to build a team, and we have to come up with an experimental design. So when we think about a campaign, we have to develop an observational strategies. What do we really need to get? What needs to be successful during a field campaign? So, and the scientific objectives are always on top of the key criteria. So we needed to look at the upwind conditions. So we needed to find a good place to launch radiosondes on upwind of the mountain. Then we already decided that Doppler LiDAR is the way to observe the flow structures. And then we needed cloud observations, and we were planning to use webcams to detect those. Then there's always technical aspects and sometimes constraints to a field campaign. I luckily had a successful proposal to upgrade our LiDAR to a stronger version. I had a radio sound system that I could bring from back in the University of Utah where I was working. And I had experience in remotely running the LiDAR systems. But we did have the constraints that we had really limited resources and we had a very small team size. Then other constraints were, of course, on the topography. So we needed to find places where we could actually have an instrument, put the instruments that was accessible, where we could service it. If things were happening, we could refuel it safely under different weather conditions. We needed to have safe shelter, and we were asked to avoid the busy tourist season, but also, of course, didn't want to get covered by the first 2 meters of snow as winter sets in. And we had to deconflict the airspace. So launching radio sounds in a place where there's lots of helicopter traffic, both for tourists, but also mountain rescues continuously. And we were asked to keep this experiment really low key. So those were the challenges, and this is what we then did to build a team. So Volkmar brought from the University of Mainz Marius to Switzerland. You see him here, and he was mainly running the models. But with him came Dominic, a really extremely interested geology student who was eager to also learn how to launch weather balloons. And then on the right-hand side, we have Hendrik Huwald, and he was really important as our Swiss partner to do all the negotiations with the local stakeholders. And in Switzerland, it's really important to understand their customs and to speak the right dialect. And all of this was really crucial. So it's always important if you run campaigns somewhere else to have locals being involved. And then Hendrik brought Brandon, and Brandon trained Paul here to help. So they made the second radio sound launch team. So for the experimental design, we had to do some really tough decisions. We had to make some tough choices. So when you look at this complex terrain, the question is, what is a good upwind location, right? You're in the middle of the high Alps. We knew we have mainly westerly flow, so we needed to find a place towards the west of the Matterhorn. And we needed to be able to transport helium to the place. We needed to have shelter for the team staying there, and we had to it had to allow for cycling of the crew. So we looked at many of the alpine huts and ended up deciding to base the sounding locations at the Schönbühlhütte, which is north of the Zmut Valley that goes east-west here. And that hut is about is reachable on a 4.5-hour hike. The Air Zermatt had experience flying there, deliveries, so they could deliver the helium there. And the hut was closed for the season, but they have a winter shelter. And so the winter shelter, the winter quarters could be accessed by us. The next tough choices were where to position the leeward instrumentation, the leeward LiDARs. And even though this map still shows glacier, much of these glaciers have retreated. But what they leave behind is glacial till and moraine and very, very loose and dangerous rock. So the only two spaces of really solid ground I marked here in orange. Side A was really exceptional. It was like a big boulder melted out of the glacier and had views. And so the summit was about 40 degrees elevation. However, being such a good space, it was really reachable only through challenging river crossings. So the raging meltwater rivers, we had to cross boulder-covered ice. So we decided that was just a very risky endeavor to access that for over a 3-week period. So the second best site is the site B. It's on solid ground. It was actually in proximity of a hiking trail leading down from Trockener Steg, and it was also tucked away somewhat with a good vantage point towards the west. So it was hidden from the tourists that frequent that trail. So we decided that this would be the place to go. Now, due to these difficulties in access and due to having just a very limited crew, we decided that less is more, and we would focus just on a single Doppler LiDAR observation. So here you see the deployment. Air Zermatt flew in our LiDAR, a barrel of gasoline, and the site became my office for 3 weeks. We set up the LiDAR to do a variety of scans that kept cycling through. So we did 3 of the RHI scans, 1 through the summit pyramid, 1 to the left and the right, and then 4 PPI scans at different elevations to look at the horizontal distribution of the flow and determining those returns circulations, and then a wind profiles. And these scans were on a 7-minute repetition. The range gates was chosen to be 60 meters so that we could maximize the few aerosols that are in the atmosphere. And the scan speeds of the LiDAR were chosen so that the resolution, the height and lateral resolution was about 55 meters at the distance of the summit of the Matterhorn. And then we deployed 2 webcams, one with the LiDAR and one where we had hard power. That was the mountaintop station at Heerlee. And you see us hiking this in. Really simple installation with very little tools. But the cameras were really important to monitor the clouds on the Matterhorn, and also the different angles help to resolve clouds and differentiate them to maybe clouds that are at higher levels. Okay, to quickly summarize the Matterhorn observations, we had 17 days of observations with 8 cases with banner clouds. We recorded about 45 hours of webcam images of banner clouds, and the banner clouds occurred under varying wind conditions. So for my results, I will now show you what we observed and focus on flow separation, leeside flow reversal, and vertical displacement, and then want to see how these observations compare with theory. So these are accumulated or averaged LiDAR scans for the October 3 banner cloud case. And you really beautifully see here this flow away from the LiDAR. So we have strong westerly flow in this case, but you see this flow reversal in the lee. And these PPI scans here nicely see the flow separation along the ridgeline and this return circulation. So we were very happy to be able, with this LiDAR, even in this aerosol scarce environment, to make these successful observations. So how do these observations compare with theoretical guidance? So if we have a closer look at the realistic topography of the Matterhorn, we see that the steepness around the Matterhorn varies. So it depends on the inflow directions and on the distance from the summit. So the steepest slopes are near the summit, and the ridge lines and slopes further away from the mountain are less steep. So A, or the aspect ratio, is a function of wind direction and distance from the summit. So, and then based on a wavelength of the mountain wave and the leeside aspect ratio A, we can define a limiting N that separates the flow regime that allows for banner cloud occurrence or allows for leeside separation. And we can plot this N-lim for an average topography over the circumference of 2 kilometers around the mountain. So, and if we do this, we can we see that the cases we have banner clouds where they fall within this flow regime. And we nicely see here that all banner cloud cases where we observe banner clouds are actually within this regime of leeside flow separation. So, however, there were a few cases that weren't, and then we had 2 cases where we were outside this regime. So when we looked at the October 11th case, looking at this, we saw that the banner cloud was actually extremely faint and almost subvisible. I was afraid it wouldn't show up here on the screen, but it actually does. You can kind of see this here. And this kind of told us that the limiting factor for banner cloud formation could also be the available humidity. And it turns out that all these cases where we didn't see banner clouds, the 3 cases where we expected banner clouds occurs had relative humidities upstream that were well below 40% relative humidity. So humidity is definitely a limiting factor. All right, as a next step, we used the observations to validate numerical simulations that Marius had set up. So Marius now used the inflow profile from the radiosondes as boundary conditions for Euler simulations. And then he pulled out synthetic LiDAR scans, so radial velocities that our LiDAR would see upwind, to compare actually radial velocities, the radial velocity fields. And you nicely see the great correspondence of our observations with the simulations. You see the nice area where flow separation occurs. You see the reversal of the flow. And you also see nicely indicated this area of large radial velocities away from the LiDAR, indicating the flow reversal and uplift. Of course, we need to stress that the LiDAR measurements are limited, because when we have actually a cloud, the LiDAR will attenuate. That's why the coverage there is somewhat limited. So now, as a next step, we can also look at simulated case study for cases where the occurrence was within the leeside separation regime and outside of it. So regimes where the flow suggests that banner clouds are occurring or can occur, and where they don't. So the 12th of October case, that is here, when we look at the simulations and look at the vertical displacement, so that potential for banner cloud occurrence, we see that there's actually a high potential. So this, again, we use the model setup to confirm the theoretical guidance and confirm what we are seeing. On the 16th of October, we were outside the leeside separation, separation regime. And when we look at the vertical displacement during these simulations, we see that clear peaks for this banner cloud potential is also lacking. And we're seeing more that there's a separation that is further downwind, indicating that there's gravity waves and this post-wave separation regime happening. Another advantage now of these idealized or these model runs that we were able to validate with the LiDAR data is that they allow us to look at the finer scales of the turbulence. And we can, with the LiDAR, we only have one measurement every 7 minutes as we cut a slice, but our model simulations have a time step of about one second. So we can actually resolve these flow features and see how this vertical displacement is actually accumulated over time. what we also nicely see here, that in the 29th September case, this was a case under northwesterly flow, we see a deep banner cloud forming that is in the lee side and is tightly connected to the top of the mountain, while on the 3rd of October case under westerly flow, we see that the banner cloud is more confined to the upper levels, but it creates a big banner that is moving downwind and shows Kelvin-Helmholtz-like mixing structures. Now, as a next step, we can look again, compare these model results with direct observations. And in this case, we are using the webcam. And we're nicely seeing the corresponding static banner cloud that we also see in our direct, in our observations with the webcam, while on the 3rd of October case, we see this extended banner, shaped banner cloud with these Kelvin-Helmholtz-like waves spinning off. All right, so I'm already probably a little bit fast. I'm coming already to the summary and conclusions. So banner clouds formation requires a couple of ingredients. It needs this flow separation and this leeside recirculations and strong leeside lift, or this vertical displacement. Coherent vortex structures, as seen in idealized simulations, are really not required. So the other results is that this vertical displacement, these maxima in the lee are very robust to different flow conditions with respect to details in shear, wind speed, and so on. But they represent a really good measure for banner cloud potential. And these flow conditions conducive to banner clouds exist much more frequently than their occurrence might suggest. And we've seen several examples of that. And the reason is that there's, at these high elevation, there's sometimes just not enough moisture, that despite the large vertical displacement, there's no condensation. However, this can mean that dangers to mountain aviation still exists, even in the absence of banner clouds. Oh, and here's a little animation of it I meant to click. So, furthermore, despite these topographic and observational challenges, we were able, by really carefully designing the field campaign, to observe the key mechanism using upwind soundings, downwind LiDAR observations, combined with webcam images. And we could use this observational data to validate these high-fidelity model simulations by comparing radial velocities or synthetic radial velocities pulled out from the model simulations. And I want to point out, I've got a really nice feedback from one of the reviewers that this work should be a motivator for early career scientists to do observational work, showing that a relatively simple but well-designed field experiment can fill a missing gap in our understanding. So with that, I want to bring up the acknowledgement and hope that you have lots of questions for me.
Thanks, Sebastian, for that very informative and interesting seminar. Reminder to those online, you can submit your questions via Slido tab right above the video. Do we have any in-room questions?
Thanks for the talk. I really enjoyed it. In your regime diagram, when you were talking about different types of flow over the different mountains, I was surprised that there's no horizontal wind speed in that. Is there a reason why there isn't wind speed?
Sorry, there's no
horizontal wind speed. It's the x-axis is n and the y-axis is aspect ratio.
Yeah, but
Or am I missing?
U is included in the inverse fruit number.
Gotcha. But
So the inverse fruit number, or non-dimensional, you might refer to as
yeah, I
non-dimensional
know what the fruit
mountain
number
height.
is. But in your regime diagram where you were predicting the type, that one on the right hand.
So here the inverse fruit number is
okay,
a
okay.
capital N.
That's
so
not-
sorry,
okay.
there's this. The Brunt-Weissala frequency
Never mind.
is the
Thanks.
the
Yes, that makes perfect
non-cursive
sense.
N. So
That makes
this is
perfect
really
sense.
the inverse fruit number, or that non-dimensional mountain height. So this is a regime diagram for these two non-dimensional
Yeah.
parameters.
Makes sense. Thanks.
So.
This was actually really interesting. You showed this plot a couple times, but on a couple you showed the like a polar plot showing where there was leeside flow separation potential, I think based as a function of wind speed, and there was a dark black line that I think was indicating whether something was potentially separating or not. Was that like something that fell out of just a bunch of model runs or theory, or kind of how did that black line show?
Sorry, I think I went a little fast on that slide, so I'll go back to this.
I marked slide 43 as
Yeah.
notes, but
All right. So this is basically like,
yeah, black
let's see
line.
here. Oops. There's black line. So basically what we can do is we can look at A, right, the mountain aspect ratio, and we can kind of average this over 2 kilometers. And this is chosen because this is kind of the circumference of the Matterhorn, right, where it is kind of that summit pyramid. And so we can calculate an average A for this approach angle, or it's actually the leeside slopes that are important. So this A will tell us what inverse fruit number cannot be exceeded to allow us to be in the regime for leeside flow separation to occur. So this is kind of the threshold. So if we are outside of this regime, we don't expect banner cloud formation, or we don't expect the flow regime to be conducive to banner cloud formation, while within the regime, we expect it to be. So and this is then where we this is where then we can look at our observations. So these are basically the radiosonde ascents that we chose, and we see where these fall. So, and then based on these, we could show that the non-banner cloud occurrences are due to very low relative humidities. So despite the potential and the uplift that we then see in the model, banner clouds can form, right? And when we were outside, we don't expect the flow to be conducive. And we, Marius did a model run for this case, which I showed, which clearly didn't show enough vertical displacement to support banner cloud formation.
Thank you.
Thanks for letting me clarify this, Kevin.
Great talk, Sebastian. So one way to look at this, and as you mentioned, flow around the mountain generates lift, and that implies a pressure drop, which would imply condensation. So presumably you weren't able to measure a pressure drop, but did you look at it in terms of the simulations and think in terms of that as part of the mechanism?
So I unfortunately did not look at pressure changes within the simulated field. So I can't really give you an answer to that, Sue. But if you were interested in this, I could definitely follow up on it, and we could test it further. And all the data and all the model simulations are also freely available and can be downloaded.
Thank you.
I don't know if you want to comment any further on Steve's question.
Oh, Steve has the same question. So, yeah. Hey, Steve, glad you could call in from Mexico. So, yes, so I do not have, I mean, I could speculate. I mean, there is the assumption of lower pressure, right? And that could have an effect. But I really think that the lift is the overarching factor that plays a role. You might also, these simulations, I also have to say, are dry. So they are dry simulations. So we're really only looking at the displacement. And so if you have condensation, you would also have latent heat release that would rather enhance the cloud formation. So, but it turns out that this displacement field is a really good value to express that potential for Banner cloud to occur independent of maybe the occurring relative humidities.
Yeah. Sebastian, that was a very nice talk. I certainly enjoyed that. I have a question. You have radiosonde profiles upwind, so you have the moisture profile upwind.
Yes.
And on the lee side, you have the height of the cloud base. Could you use that to estimate your vertical displacement?
That is a good question. I suppose you could, yes. I mean, the problem is, you know, you don't necessarily in the inflow, you know, if it's very uniform, you know, you don't necessarily know where what the trajectories are. But in combination with the model simulations, that is definitely something that could be doable. Yes.
You and Tony, and then Chris.
Thanks, Sebastian. So early in your talk, you showed some numerical simulation results where you said you were unable to reproduce the recirculating flows in the lee of the real terrain as opposed to the fake terrain. And then all of a sudden, later in the back end of the talk, you're reproducing them as you might expect. And I'm just curious what you think is different.
I think I must have misspoken then. So there are recirculations, but they are not organized. So what I meant to stress is, like, in the real topography, there are recirculation, there are eddy structures, but they are not. They break down, right? So you don't see them. They are eddy structured, but they're over time they are mixed. They're not organized in an organized fashion. But nevertheless, there is a return flow and the lift that leads to that potential. Does that clarify?
Maybe I misunderstood your statement in the early part of the talk.
Thank you for letting me clarify that.
Hi, Sebastian. Nice to talk. I appreciated the logistical considerations with making the field deployment.
Thanks. That's part of my job.
One of the things I note with the times of the banner flags is all of those seem to happen in the daytime, and I'm wondering if that's temporal related or just the time scale of how long the field deployment was. And going along with that, what percentage do you think the moisture that leads to the banner flags is coming from sublimation or evaporation from the top versus moisture upflow of topographic lifts?
So let's see. Let's go back for your first question first. You asked about the diurnal cycle. So there are studies of the diurnal cycle at other mountains. We just didn't feel like we had enough cases to really make a statistics and tell you they were occurring more or less. They can occur and they can be observed throughout the diurnal cycles. But for us, these webcams are also not working very well at night. They are kind of made to detect burglars in the parking lot. And they are not working well during the night. So that was just a limitation. of that. But they do occur, and sometimes they last later in the night, and we can see that, of course, in the LiDAR backscatter. So in those circulations, we can see it. The second question you had was about the moisture and where the moisture came from. So I can't really speculate on that. Typically, under these these occurs when you have strong westerly flow, right? And so there's a lot of mixing and overturning in this complex terrain. We've seen stronger gradients in moisture in the early morning when we see, thermally driven circulation out of the side valleys that are impinging, or we're seeing more stable layers attached, associated with the local terrain around the Schönbühlhütte, where we knew we had to be a little bit careful, and they were probably less representative for the flow that's really interacting with the mountain.
All right, Chris, and then we have a question online from Elise.
I'm back.
Yes. I'm glad you're excited about this topic.
Oh, yeah. I enjoy
I thought you were.
Have you, I don't have the question well formulated, but I was thinking about mixing on the lee side and thinking about the pressure perturbations, dynamic and hydrostatic, as well as the banner cloud formation. To what extent does mixing affect the formation of cloud? As it's swirling around, it's probably mixing with drier air from up above, and that might suppress the cloud. And I'm also curious, what's the final level at which these parcels end up being at? Are they permanently lofted, or do they must return back to where they were lifted from?
Yes, they're typically at that elevation. Of course, we haven't really looked at how what happens downwind, but once they're there and they get kind of sheared off, and the mixing is definitely an important criteria, right? If you have your strong gradients in that banner cloud potential, so in this vertical displacement, right? If you have strong gradients, they are basically, if you assume you have a constant humidity profile flowing in, they basically tell you about the humidity gradient. And so as you have mixing at the edges, that will tell you how long that banner can actually persist downwind and will affect the shape of the banner cloud. So mixing is absolutely a critical feature in that moisture gradient, which probably is well represented in the gradient of your vertical displacement field, is decisive for that.
Yeah, thanks.
So we have a related question from Elise, follow-up to earlier. In regards to the comparison of observed and simulated flows, do you think that better observation measurements would have created a comparison that looks even more like the simulation results? Or do you think a more realistic simulation would have brought the simulation closer to the observations?
All right, thanks, Elise, for that question. I actually think that the comparison is remarkably good. So I would argue for somebody who takes observations regularly that this intercomparison is quite amazing. Of course, there's gaps in the observations due to the fact that we have attenuation of the LiDAR or other comparison, and I really focus just on one comparison. We have many cases where we can do these comparisons. But I think what actually made it good was to actually compare the measurements that the LiDAR is taking, so that we extracted radial velocities from the model field, right? If we had two LiDARs, we could actually look at the flow and could have compared wind vectors, right? And I think by using these synthetic scans from the model, we actually made it easier and much more meaningful to compare models with the observations.
So in our final couple minutes, we have a quick question from Elise on how did the potential public outreach opportunities go?
You probably saw this. So I didn't mention this in the talk. Of course, we were thinking about outreach. It's always a lot of fun to actually get the public involved. But we had clear guidance from the commune of Zermatt to keep this really low key and not to attract any media. And they said they wanted to avoid a commercialization of the Matterhorn. And so, but we were really, so we invited EPFL, a class of EPFL, to the field site, and it was really fun to have little talks by Volkmar and Marius on the theory and modeling, and I presented the LiDAR there to a group of students in the field. And then at Schönbühlhütte opened actually for one weekend to welcome a couple of classes from a high school. And so we used that opportunity to introduce our project to the high school class, and the students got to launch one of the balloons, and that was a great outreach opportunity, even though it wasn't really planned or scheduled for. But that was the challenge that we had. We couldn't really advertise into this because we were restricted to keep this small.
Sure, makes sense. So Mary Barth has a forward-looking question. She says, very nice talk. Do you have plans to extend this research? And if so, how?
So there are still a lot of questions. So when you look at the data and I look at these banner clouds and there's these regime transitions, there's also a phenomena where you have cap clouds forming, right? So it also, I didn't talk about the temperature profile and where stability gradients are in the profile. And depending on the evolution, we actually can see transition between different cloud types, so from a cap cloud to a banner cloud, which really tells you a lot of the dynamics and the thermodynamics in the atmosphere and how this is changing. There's fascinating images where we see a cap cloud forming, but a dry banner cloud. So this is a banner cloud type of flow that is occurring in the lee of the mountain, but it is dry, there's no condensation, and that mixes into the moisture from the cap cloud, so there's a clear moisture gradient, and we see actually the features of the top, the mixing features on the top of the banner cloud that leads to an erosion or dissolution of the cap cloud. So there are a couple of really fascinating case studies that could be pulled out. The other phenomena that could be related is to maybe look, especially here in Boulder, to look at rotor clouds that are occurring during our downslope windstorms. So floated an idea of maybe in Marshall, one could use dual Doppler LiDAR to look at rotor clouds or look at the rotor motion in the dry air when no rotor cloud is visible and do a similar simulation there. And that has, of course, applications to us, power shutdowns, fire weather, and all these fun things living in the downslope windstorm flow environments.
Sure, lots of ideas. Well, that concludes our hour, so let's thank Sebastian one more time.